Hello everyone, welcome back to our course. In this lecture, we'll talk about adversarial machine learning.
Until a few years ago, machine learning did not work very well on many meaningful tasks, like object recognition. It was rather a rule of thumb that machine learning failed. Since then, the machine learning advanced to the next step, and now it can outperform even humans. For example, not only does a neural network classify the image on the left-hand side as a dog, but it also correctly specifies its breed as bull mastiff. Similarly, the cat breed is classified as tiger cat. However, machine learning has not yet reached human-level performance, because when confronted even with a trivial adversary, it fails dramatically. These have implications that can be preventing us from deploying machine learning models in safety-critical applications, for example, in self-driving cars or fraud detection. We will review machine learning in the adversarial setting. We start our machine learning pipeline from collecting the training data. In this example, we want to distinguish dogs from cats. We create a simple classifier that uses only two features: how pointy or floppy the ears are, and how long or short a tail is. We extract these features from the training set and deploy the model. If we provide the picture of a cat to the classifier, it identifies that it has pointy ears and long tail, and the classifier correctly returns the label cat. However, if we provide images that are out of distribution and that classifier has not been trained on, for example, an image of a stork, then the classifier cannot extract the relevant features and cannot make any meaningful predictions. This illustrates that as soon as the model is deployed, especially in the adversarial setting, we have a mismatch between the train and the test distributions. The adversary presents us with the worst-case test distribution drift. In the adversarial setting, the image on the left-hand side of a dog can be slightly perturbed in a way that is imperceptible to a human eye. And this is done by adding the noise presented in the middle, and we magnify the noise 100 times to be visible. Now the neural network can be fooled and classify the obvious picture of a dog as a tiger cat. In the broadest sense, by adversarial perturbations, we define small imperceptible changes to the input that alter model predictions. The most common definition of adversarial examples assumes that an adversary can change the classifier decision without changing the semantic of the input. In this example, the model classifies the digit correctly as 3, but adversary fools the model by slightly changing the image, which is now classified as 5, and this is shown as the blue dot. The X star represents the perturbed input X by epsilon bounded noise. The oracle's decision, meaning the true label of the input, remains unchanged. In this review, we will focus on such epsilon bounded adversarial examples. The adversarial attacks can be divided according to the threat model into the white box and black box attacks. First, we'll talk about the white box attacks. The white box attacks have access to the model architecture, parameters, and gradients. The gradient is used to find the direction to manipulate the input so that the loss for the correct class Y is increased and the input is misclassified. First, we'll consider the attacks in the L-infinity norm, where we want to minimize the maximum change in every dimension. The fastest white box attack, called FGSM, takes a single gradient step. It computes the gradient of the loss function with respect to the input x, takes its sign, and then tunes the maximum distortion with the parameter epsilon. This attack was further enhanced by adding a randomization step at the beginning of the algorithm, where we perturbed the input with, for example, the uniform noise bounded by epsilon. The basic iterative method, abbreviated as BEAM, improved upon R plus FGSM by taking multiple smaller FGSM steps. Finally, this iterative adversarial attack was further strengthened by adding multiple random restarts and is called the projected gradient descent, abbreviated as PGD. This is a visualization of the PGD attack. We define an epsilon ball around the input x. Then we take the steps based on the gradient direction. If in a step k, we use the gradient to find the next point and go outside of the epsilon ball, we search for the nearest point on the surface of the ball. Then we project back on the allowed region. Next, in case of black box attacks, we do not have access to the model parameters or the gradients. We divide the black box attacks into score-based and decision-based. The score-based attacks expect meaningful scores, such as probabilities, so outputs from the softmax layer, or logits, which can be used to approximate the gradient and find the adversarial perturbation. For decision-based attacks, only the final label returned by the model can be accessed by an adversary. First, we'll talk about the transfer-based attacks, which are decision-based attacks. So, this attack consists of two steps. The first step is a reconnaissance step, where we extract a copy of the target attacked model. This copy is called a surrogate or a substitute model. We create the surrogate model by selecting the queries so that we can learn as much as possible about the decision boundaries of the attacked model. We bootstrap the process with a few initial images and then use the surrogate model to guide us which next queries should we send to the attacked model. The final step is to find the adversarial noise using the gradient computed on the surrogate model. This attack is effective since adversarial examples usually transfer between different models. Next, we present an example of a score-based attack, which is called SIMBA, a simple black box attack. To explain the main intuition behind SIMBA, it takes about 60 seconds. First, we select a pixel. This is done uniformly at random and without replacement. Then we either add or subtract an epsilon value from this pixel. Such perturbed images are sent to a classifier to obtain some form of scores, for example probabilities, assigned to the correct class Y. Finally, we either select the perturbed image that decreases the score of the correct class the most, or if the input image X has the lowest score, then we leave the pixel unchanged. We iteratively repeat the process of modifying the pixels until the input becomes adversarial. This is a form of an L0 attack, where the adversary aims to change as few pixels as possible. The main advantages of SIMBA are its simplicity and efficiency. This is an example of an attack on the Google Cloud Vision API. For the initial image on the left-hand side, the classifier returns labels related to the camera accessory. The goal of the attack is to replace the top three concepts with guns and weapons. SIMBA's success rate in this case is 70% with a budget of 5,000 API calls that costs about $7.5. The best other attack has only 25% success rate under the same budget. In general, the black box attacks provide us with practical attacks against cloud vision APIs. Adversarial examples exist also in the physical world. The authors of this attack generated and printed pictures of the adversarial examples. Then they took photos of these examples with a smartphone camera and classified these images. The classifier was fooled and labeled this picture of a washer as a safe or a loudspeaker. The authors of this attack 3D printed a turtle. An unperturbed 3D model is classified correctly as a turtle nearly 100% of the time. When the turtle is adversarially perturbed, it is classified as a rifle at every viewpoint most of the time. This method introduced the EOT technique, which stands for expectation over transformation, so that adversarial examples remain adversarial over an entire distribution of transformations. We'll cover this method in detail when we talk about adaptive white box attacks. This is an illustration of the audio attack, where given any waveform, we add a small perturbation that makes the result transcribed as any desired phrase. The latest audio attack produces generic adversarial examples against automatic speech recognition systems. This latest attack remains robust in an over-the-air setting, where adversarial example is not a direct input to the system, but it is played from a sound source. This latest attack leveraged the room impulse response, which is the transfer function of the room between the sound source and microphone. Up to now, we have seen many ways how to attack ML models. Now, what are the ways to defend them? There are 4 main categories of defenses. The first type of defense is based on the pre-processing of inputs, and they are perturbed, for example, by compressing them. Unfortunately, this method is usually ineffective. The second approach is to add some form of randomization, either to inputs or internal layers of neural networks. This can be done by injection of random noise, for instance, Gaussian or uniform noise. The third approach projects the input samples onto a learned manifold using generative models. Finally, the adversarial training augments the training data with adversarial examples. In this review, we focus on this last form of defense. During a standard training of a model, we change the model parameters theta to minimize the loss. During an attack, we modify the input x with a small perturbation delta to increase the loss for the correct class y. Adversarial training combines the training process with generation of adversarial examples. For each input x that is clean, we find an adversarial example that is then fed into the training process with the correct label y. Here we present performance of adversarially trained networks against PGD adversaries of different strength. The x-axis represents the strength of the PGD attack, and the y-axis represents the model accuracy. The network is trained against the PGD attack with the allowed max distortion of epsilon equals 0.3. This is denoted as the vertical dashed line in the plot. For epsilon less or equal to the value used during training, the performance is much better than after the threshold. And we observe similar trends for other datasets and models, for example, in this case, for the CIFAR10 dataset. 7 of 9 defense techniques accepted to ICLR 2018 were broken using white box adaptive attacks. The most robust defense was the adversarial training. Many other defenses apply security by obscurity, which in this case is usually by gradient masking or obfuscation. And this can be done by hiding or randomizing the gradients in some way. And if the gradients are randomized, then they are not useful for an attacker. One of the ways to deal with this form of gradient masking is by creating adaptive attacks. For example, by EOT, the expectation over transformation method, which was first used to produce adversarial examples in the physical world by 3D printing. In the EOT method, we compute the gradients many times, usually 10, in the forward and backward passes. We accumulate the gradients, and here it is done in the grad noise variable. At the end, we average the gradients to get a more accurate gradient. So the adversarial training occurs to be one of the most robust defenses. There are many new proposals to further improve this method. Let's analyze a few of them. For natural data, such as simple decision boundary might be sufficient. However, if we allow an adversary to perturb the input, here represented as L-infinity balls around natural examples, then the adversary can find adversarial examples that cross the simple decision boundary. So what is needed is a more complicated decision boundary that is staircase one. Conceptually, models with higher learning capacity can have such complex decision boundaries, and because of that, they can be more robust. However, we observe diminishing returns for larger models. We use overparameterized deep networks for natural data, but these large models do not have enough learning capacity for adversarial training. This is because adversarial data smooth neighborhood of natural data, which consumes much more model capacity. Thus, we should utilize the capacity judiciously. This can be done by reweighting the training data points. This is an illustration of a technique which assigns larger weights to the adversarial data, shown as larger red plus or minus signs, whose natural counterparts are closer to the decision boundary, denoted in lighter blue. Analogously, smaller weights are assigned to adversarial data that are found starting from natural points further away from the decision boundary. This method was shown to significantly improve the standard adversarial training. For the identical parameter count, deeper models can perform better. This graph represents robust test accuracy on the y-axis and number of parameters on the x-axis. Different types of the wide residual networks were trained on CIFAR10 data while changing their depth, the number of layers. First, these results further corroborate the claim that larger models are more robust. Second, if we consider the models with the same number of parameters, then the models with more layers, in this case with let's say 46 layers, are more robust than models with 28 layers. One of the crucial aspects of a given architecture is the selection of the activation function. The choice of activation function also matters in terms of the robustness. This graph shows the robust test accuracy on the y-axis and clean test accuracy on the x-axis. These experimental results indicate that smooth activation function /SILU performs best in terms of the robust test accuracy. On the other hand, other smooth activation functions, for instance soft plus, do not necessarily correlate positively with robustness in these experiments. While ConvNets have revolutionized computer vision, the latest results indicate that models tailor-made for imaging tasks may be unnecessary or even suboptimal. With ever-increasing dataset sizes and the continued development of unsupervised and semi-supervised methods, development of new vision architectures that train more efficiently on the datasets becomes increasingly important. The vision transformer is a preliminary step towards a generic, scalable architecture. It can solve many vision tasks and probably even tasks from other domains. We have considered the architectures for robust models, and now we'll analyze how to achieve robust generalization by using more data. It was first shown that the additional data from the ImageNet dataset can improve robust accuracy of models trained on CIFAR10 data. Next, the CIFAR10 dataset was augmented with 200,000 and 500,000 unlabeled images that were sourced from 80 million tiny images. And this further improved the robustness of the models. However, there is a limit on how much additional unlabeled data can improve the robust accuracy. The table represents accuracy under the L infinity-based attack on CIFAR10 data as the quantity of unlabeled data is increased. The latest results show that the robustness can be improved when we add up to 500,000 images for the CIFAR10 dataset. However, increasing the number of additional images further to 1 million is detrimental. The reason is that as datasets increase in size, the images they contain become less and less relevant to the CIFAR10 classification. Thus, there is a trade-off between the quantity and the quality of the extra unlabeled data. Once we collect the additional data, the question is how to use the data. One of the aspects is related to tuning the ratio of labeled to unlabeled data per batch. The graph shows robust test accuracy on the y-axis against the labeled to unlabeled ratio per batch on the x-axis. The optimal ratio is 3:7, which intuitively shows that if we have 10 times more unlabeled data, then we should give proportionally more weight to the unlabeled data during our adversarial training. We can also gain some insight into the internal workings of adversarial training from the perspective of channel-wise activations. The magnitudes of channel-wise activations are represented on the y-axis. The x-axis represents 512 channels at the penultimate layer of ResNet 18 trained on CIFAR10. The standard training is shown on the left-hand side, and the adversarial training is shown on the right-hand side. In each plot, the magnitudes are averaged and displayed separately for natural and adversarial test examples. The 512 channels are sorted in descending order of the magnitudes. The attack used here is PGD with 20 iterations. For standard models, the activation magnitudes of adversarial examples are higher than that of natural examples. The adversarial training decreases the activation magnitudes of adversarial examples. Another difference between the standard training and the adversarial training is the channel-wise activation frequency. The y-axis represents how often a given channel is activated, and similarly to the previous slide, the x-axis represents 512 channels at the penultimate layer of ResNet 18 architecture trained on CIFAR-10 data. A channel is determined as activated if its value is larger than a certain threshold. The channels are sorted in descending order according to the activation frequency by natural examples. For the standard model on the left-hand side, the adversarial examples activate the channels more uniformly, and they tend to frequently activate those channels that are rarely activated by natural examples. Additionally, adversarial examples activate fewer times the channels that are activated frequently by natural examples. The low-frequency channels are usually so-called non-robust channels, and they usually correspond to redundant activations. They are less important for the class prediction. The adversarial training forces the channels to be activated in a similar frequency by both natural and adversarial examples. Based on these results, there is a new method that tries to even further align the activation frequency of channels by suppressing the redundant activations during training to make the models even more robust. Another issue with adversarial training is its efficiency. There are many new proposals to make the defense more efficient. In the standard adversarial training, first we find adversarial examples using PGD attack with many iterations. Then we use the found examples to train the model. The so-called free adversarial training proposes to merge these two stages and introduces free optimizations. First, it uses a single backward pass to update both model parameters as well as the adversarial perturbations. It also trains on the same mini-batch through many iterations, where the inputs become stronger adversarial examples with each iteration. Finally, it warm starts the next batch by perturbing it with the perturbation found for the previous batch. We compare standard adversarial training proposed by Mondre with the free adversarial training starting from the same clean accuracy of about 87%. The free adversarial training yields a slightly less robust model by about 4%, but it can be trained about 7 times faster. It occurs that the warm start from the previous batch can be replaced with starting from a non-zero random initial perturbation. The fast adversarial training generates gradients for inputs using larger FGSM step size with random initialization. It uses mini-batch only once, and it cannot simultaneously compute gradients for inputs and parameters. In this graph, the x-axis represents the number of epochs for training, and the y-axis is the error. For the standard training of neural networks, shown as the red and green lines, we can train the models as long as possible without harming generalization. On the other hand, the adversarial training, shown as the orange and blue lines, overfits to the attack used during training, and it does not generalize to other attacks. The robustness error dips immediately after the first learning rate decay, and only increases beyond this point. A simple remedy to avoid the catastrophic overfitting is to apply the early stopping. If we compare the free and fast adversarial training based on the same robust accuracy of about 46%, the fast method can be even 2 times faster than the free method. We saw that adversarial training overfits to the L-infinity based attacks. Actually, adversarial training on the L-infinity based attacks makes model even more vulnerable to other types of attacks. To overcome the problem, one proposal is to train the model on the strongest adversarial example for a given input. This is called the max strategy. The attacks are carried out in L1, L2, or L-infinity norms. We plot the number of epochs for training on the x-axis, and y-axis represents accuracy. The horizontal dashed lines show the accuracy of models trained and evaluated on a single perturbation type. The accuracy of the model is about 99.9% on clean data. However, it drops to about 91% for the L-infinity based attack, and then to a bit more than 76% in case of L1 and L2 based attacks. When we train our model and test against the strongest adversary in multiple norms, the accuracy of the model drops further down to only about 52%, which is depicted as the brown dashed line. The last results lead us to many new problems. For example, building an effective defense, even for the MNIST dataset, might be very expensive, let alone building robust defenses for the large-scale datasets such as ImageNet. It also showed that the gap between the train accuracy and the robust accuracy is even wider. Last but not least, the adversarial training allows us to classify unrecognized images with high confidence. The question is, why is it hard to build a robust defense against adversarial examples? The adversarial training is rather a brute force method, and it requires us to train on many possible perturbations to be fully robust. In practice, the computational cost of such a defense is very high. Next, it is also difficult to construct a theoretical model of how the adversarial examples are crafted. Adversarial examples are solutions to an optimization problem that, for example, in case of neural networks, is nonlinear and non-convex. Thus, it is very hard to make a theoretical argument that a given defense will be robust against all possible attacks. Adversarial examples require models to produce good outputs for every possible input. However, the number of possible inputs is humongous, and usually the machine learning models work well on a small part of the all possible inputs. Finally, current defenses are not adaptive. For instance, if an adversary detects that a defense masks gradients, then he or she can switch from a white box attack that leverages the gradients to a black box one that is a gradient-free method. So if a given defense closes some vulnerabilities, it usually leaves others open. An adversary who uses an adaptive attack seems to have the advantage in this case. Now let us take a step back and ask, why do adversarial examples exist in the first place? The prevailing view has been that adversarial examples stem from some quirks of the models that will eventually disappear once we improve training algorithms or provide larger scale data. The other explanation is that adversarial examples are a consequence of the input space being highly dimensional. The latest work suggests that there exist non-robust features that are highly predictive, yet brittle and incomprehensible to humans. There is no one definitive answer to this question, and it remains an open problem. It occurs that we can train high accuracy models only on high frequency features that are incomprehensible to humans. In the graph, the y-axis represents accuracy, and the x-axis is size of a filter that we use to either extract low or extract the high frequency features. and we can do it with either a low or a high pass filter accordingly. Let us focus on the red line that corresponds to allowing the models to be trained only on the high frequency features. Despite this restriction, models can achieve above 50% top 1 accuracy on the ImageNet data using features in the input that are nearly invisible to humans. As is shown on the right-hand side, the high-pass filtered images needed to be normalized in order to be properly visualized and so that we can see the high-frequency features. And the previous results can lead us to the next notion of robust and non-robust features. So one explanation of why there exist adversarial examples is from the perspective of a data set. So here the claim is that there are robust and non-robust features in our data. For example, for the classification task to distinguish between dogs and cats, we have robust features such as ears and tail, and some non-robust features. Let's say these are X, Y, Z that are meaningless to humans. However, when we train our models, we want the models to minimize the training loss and maximize the test accuracy. So the models can use all the available features towards fulfilling this task. This is rather not a surprise that if we define the learning task in such a way, then the non-robust features can occur to be helpful. The result of this is that our models can use the non-robust features and then they become vulnerable to adversarial examples. Thus, robust training should prevent models from depending on the non-robust features. One of the intuitive explanations is that adversarial examples are caused by small measure regions of adversarial class jutting into a correct decision region. This model is commonly accepted because the inputs remain correctly classified when perturbed with small random noise, for example, uniform or Gaussian noise. However, you can also easily find the attack vector that moves the inputs to decision regions where they become adversarial. This motivates a very natural defense strategy that we discuss next. The idea is to smooth the decision regions by adding Gaussian noise to the input and selecting the majority class of the classifier over this noise. Here on the left-hand side, the dotted circles represent the level sets of the Gaussian noise distribution centered at the input data point. F of x refers to the class outputs for the initial classifier, and g of x is the new smooth classifier. So how do we create it? We sample random Gaussian noise epsilon that we add to the input x. And for such randomly perturbed input, we compute the majority class y. Now we have this new dashed black line on the right-hand side that represents the robust decision boundary. The question is, have we achieved the robustness? It occurs not. There is another notion of adversarial examples that are called the invariance-based adversarial examples. They are epsilon bounded from the initial input. However, the real label of the perturbed input changes with the small epsilon ball. The robust classifier is too constant in its predictions and incorrectly assigns the old label 3 that is no longer correct.
For supervised learning, adversarial attacks produce imperceptible changes, delta, to an input x that result in the model predicting an incorrect label y. To increase robustness, adversarial training incorporates the perturbed data with the correct label into the training data. Yet, since the self-supervised learning, abbreviated as SSL, operates without labels, the standard adversarial training is not applicable. The initial method towards robust SSL introduced a purifier network to defend against adversarial examples, which attempts to recover the original input from an adversarially perturbed version before inputting it to the encoder. However, as we learned in the previous slides, the adversary might just backpropagate through the purifier network to find the adversarial examples. Thus, this method was not successful. The general rule of thumb is that the methods based on recovering the inputs, introducing some form of compression or additional perturbations, they are just not effective. The natural way to solve the problem is to introduce the adversarial training into the self-supervised training. The idea is relatively easy. During adversarial training, we maximize similarity in the embedding space. This is between these latent vectors z sub I, z sub j, and z sub k. And this is to minimize this latent space vectors between two differently transformed examples t sub x and t prime sub x, and the adversarial perturbation t of x. To find the adversarial example in SSL, the robust contrastive learning method introduced the instance-wise attack, since the class-wise adversarial examples are inapplicable to the unlabeled case we target here. To elaborate on the instance-wise adversarial examples, we have to start from the contrastive loss function. In this function, we want the similarity between the representations z for positive samples to increase and for the negative samples to decrease. This is the inference loss, a loss that was used in SimCLR SSL framework, and this is similar to the soft nearest neighbor loss that we defined in the last lecture. Given the loss function for SSL, now the question is how to generate adversarial examples. So we denote the adversarial example here as t of x to the power of I plus 1. So this is in the I plus 1 iteration, it's similar attack as PGD. The main idea is that given a sample of an input instance x, we generate a perturbation within the epsilon ball to fool the model by confusing its instance level identity such that it mistakes the example x as another sample x prime. So this is done by generating a perturbation that maximizes the self-supervised contrastive loss for discriminating between these instances. T of x and t of x prime are transformations of this image x with stochastic data augmentations, and t of x neg, this negative, are the negative instances for data point x, and these are examples of other samples x prime. So in simple terms, within this sign parenthesis, we compute the gradient of the loss with respect to the given image augmentation, p of x, and then change the augmentation to be far from the positive pairs and closer to the negative pairs. And we take into account that the input change can be only within the L infinity epsilon ball. Finally, we define the adversarial learning objective to learn robust representation by self-supervised contrastive learning. The adversarial min-max learning objective for an instance-wise attack follows the min-max formulation of Mondru et al. That was presented earlier in the lecture. T of x plus delta is the adversarial image, the theta are parameters for the encoder, and the pi are parameters for the projection head. We find the perturbation delta in the epsilon ball that maximizes the contrastive loss value. Note that here we generate the adversarial example of x using a stochastically transformed image t of x rather than the original image x. This allows to generate diverse attack samples. This adversarial learning framework is essentially the same as the supervised adversarial learning framework, except that we train the model to be robust against the instance-wise adversarial attacks. The loss function for the robust contrastive learning is a simple modification of the contrastive learning objective by using the instance of adversarial examples as additional element in the positive set. The total loss combines the raw CL loss with the adversarial learning objective. The lambda parameter is a regularization term. One of the limitations of this method is that the adversarial training has to be done from scratch within the contrastive learning. In contrast to training from scratch, the latest method, called decoupled adversarial training, abbreviated as DACL, fine-tunes existing encoders. In stage 1, this is just the standard SSL, self-supervised learning training. Then the encoder obtained in stage 1 is fine-tuned in stage 2. For increased robustness in stage 2, we use a knowledge transfer from a pre-trained encoder to robust one. The objectives for the distillation are, first, match the distilled encoder representations to those of the pre-trained encoder, and this is ensured by the high cosine similarity between the representations of the teacher and student. Second objective of DACL is to bring the distilled encoder's representations for adversarial examples close to their clean counterparts. The adversarial examples are generated in the same way as in raw CL, so we generate them on the pre-trained encoder to maximize the distance of adversarial representations from the original samples. By decoupling the encoder pre-training from increasing its robustness, DACL provides high computational efficiency in comparison to prior methods like raw CL, and also it was shown to obtain state-of-the-art robust performance. So where do the savings in the training time come from? Ignoring specific implementation details, the basic rationale is as follows. SSL typically requires m times more iterations than their supervised counterparts due to the m augmentations generated for each input. Then adversarial training is often n times slower than standard training, since we need n PGD steps to generate adversarial example. Combining SSL training and adversarial training into a single stage, as in raw CL, makes it m times n times slower. The DACL method makes it only m plus n times slower due to this disentangling effect. So we have separately in stage 1 self-supervised learning, and then in stage 2 we have only this fine-tuning, which is just pseudo-supervised adversarial training.
There are many other open problems in adversarial machine learning. First, we would like to define adversarial examples using certain norms. We also have to answer the question, what really causes adversarial examples? How can we create more robust models? Do they need more capacity? Should we create new architectures? Do we also have to sacrifice the performance for legitimate users? And if so, how much? So that we can train robust models. Many of these important problems remain open.
With that, thank you very much for your attention.